all of you. As uh, told by Rajiv sir, that this is the some talks on the microgrid and RA integration system. So basically, today's scenario, as you know, that the power generation profile is being changing. Like a few years back, after a decade ago, we were talking about if some fossil fuels like oil systems and coal, if they get consumed, then what will be the future of power generation? Okay, so at that time, there is a talk of some renewable into the system or wind energy or like geothermal energy is being taught, but those are only in literature. Right now, this is the time when it is actually growing in commercial way, and today you see there are lots of thrust on the solar photovoltaic power generation, like lots of private player as well as uh, some PSUs as well as some individual startups are coming in this field. Okay, so like in conventional power generation, there's a standard setup, and you can't deviate much from there. We have so many limitations. Like basically in some smart grid or in modern system, there's a computational requirement, and before the computational requirement is very critical things, because that needs some standard setup. But right now, as the computational capabilities of chips is increasing, this is going to the distributed. Like you may have seen that a smart bulb, a smart fans, or a smart all those controllers and smart inverters in home systems. So as the computational capability is increasing in the system, you can go for more smarter system setup. As far as the renewable energy is concerned, so basically why we need this renewable energy setup for smarter integration, because it is much different than conventional power generation. In conventional power generation, you have one power source, that's powerhouse, and it is distributed through various network to the end consumer utility. But in the modern system, in the distributed network, like photovoltaic generation, the generation point itself is distributed to so many places. So the integration to the end-to-end user is more complex and more computational capability is required. So as we go in the this presentation, you will see that how it is. You will see more insight about how this whole system is being framed. Okay. So see, this is a two like comparison. As you see that conventional and distributed power generation. In conventional, there is a power house like coal-fired station in NTPC, like thermal and nuclear power generation house, and it is distributed through the power grid distribution system, then state electricity board, and thereafter the end consumer, like some setup, some institutional setup, or some households. Okay, but in distributed system, the itself the energy generation and the energy consumption is being distributed and connected interlinked. So this is like it's like just like an you can imagine that how internet is connected. So there's the internet. You can generate information from one computer. You can receive information from other computer. So it is as similar like that. So if you are generating from one house, suppose you are generating from one house and consuming some other house. So it is you can see that how much complexity in the power flow, like in information flow in computer networks is there. You can take an analogy from that. So in power generation also some well-established network and network administration and the computational capability is required. Okay. So see, like about 1 decade ago, the photovoltaic cell cost is very high because there is a no volume production of photovoltaic cell. So there is a per unit means that the per watt the the setup required, the photovoltaic required for generation per megawatt is very high. So you can see the 1970s there is about $76 per watt, so is the cost, and right now you can see that in India it's about 700 rupees per unit power cost. So as the time proceeds, the power the manufacturing cost is decreasing. The volume of manufacturing increasing. Its cost is going down and down and down. Okay. So right now this is a time when it comes to the competitive level. Like the power you generate from the renewable energy in photovoltaic cell and the power you're generating from the coal-fired station is like equal, most similar. So either you can switch to the renewable energy generation, you can switch to the cost coal-fired generation. But previously, about a decade ago, it's a different scenario. So when you go to the photovoltaic generation, its cost are very high because fixed cost is very high per megawatt of power generation. Okay, so due to this, because we have to think in commercially also on the point of view, we can create a technology, very good technology, but for the sustainable of technology, it have to proven commercially also. If traditional technology is costing less than your advanced technology, so commercially conventional technology is acceptable because it has some commercial and financial terms. So right now, it's the time has come when the photovoltaic or the conventional the renewable power generation is costing is come as compared to the conventional power generation. So most of the business houses and the governments are moving toward the the renewable power energy generations. Okay, you can see this is this is the LED bulb tube light CFL. So you can see that why it is required because uh, you can see here like in just 5 and 6 years ago, you can see in India also the consumption of LED bulb is grown multifolds. So before, if some are taking LED bulb, his cost is very high, and normally people don't want to use LED bulb because of the cost constraints. But right now, every villages and even normal utility also are utilizing LED bulb. This is this is the second point of view that why we are going to the this renewable energy and smart grids because before this the filament type of bulbs now the utility the LED bulbs, the tube lights, and all are going to a smarter type. So integration is more likely to very easy because before your conventional equipment like filament bulbs or heater, those are the difficult in controlling their operations because that is not very much connected to the computing system. Now LED bulbs you can control very easily by the computing controlling. Okay, so for the smart grid and this smart grid integration, first we consider from a very basic example. So see here, this is the a typical solar generation system. Okay, so you can see here, you just identify that this is a photovoltaic cell here, and this is the terminal box. There is some power controllers is there, battery also is just there, and this is the lamp. This is the utility. Okay, so how it works? Normally, it works as this has an additional power source that is coming from the grid, and whatever the power surplus is there, you can consume from here. So this is a typical example for understanding the whole system. Okay, so see here the bulb can be operated from external power source like the grid power source. Okay, and can be used to access it. Like there's a question come here. There may be question comes here that why don't we use only the photovoltaic cell? So this is has the consumer point of view. Like suppose some the solar lights is don't have the sunlight. Suppose there's some weather the any season or some like some dark cities there. So this can be designed like when sunlight is there, then only it's work. It can be designed like that for consumer point of view. You can't keep the streets as dark if the sunlight is not there. So this has an external power to ensure the 24 into 7 hour of availability of uh, this system. Okay, so this need an external power as well as the photovoltaic cell power is there. Okay, so here you can imagine that here this is the requirement that some logic or some algorithm is there which switching the external power or the photovoltaic cell power is there to maintain the 24 into 7 availability of the solar lamp. And that algorithm is where the computational algorithms comes into the play. So see here, this is an ideal representation of this. photovoltaic energy system. Like one is a solar array, then DC current, then charge controller, then DC battery for the storage, and then DC current for the inverter, and then AC current you can use from any lamps or like fan or TV or whatever, because your main source is the AC current. Okay, so you can't use directly DC current to same circuits. So you have to convert the AC current into DC current into AC current to meet the normal utility requirements. Okay. So see here we talk about the important concept. Like in circuits, we see that there is capacitance. So suppose if a parametric point of view, if we consider bulb, so what are two important parameters of a bulb? So bulb has its the power rating, its the voltage rating, and its the its utility. Okay, we will talk about on another terms which arise to control all these parameters. Okay, very conceptual things we will discuss in details. So see, in this system, we can't suppose in house we install this system, so we can't depend only on the solar plates, because we have to make sure that the power availability is in the house 24 into 7. So we can't fully depend on the solar plates. Suppose some rainy season is there, solar plates have some technical difficulties, and if we depend only on the solar plate, on the this photovoltaic power generation, there's some outage time is there in which our electrical utility go to the shutdown. Okay, so we don't want that times that duration comes, and so that we have an external power source also in the house, and the photovoltaic generation also in the house. Okay, so for the commercial point of view, what we need, so we if we take some external power from grid, we have to pay some certain charge. That is the electricity charges per unit. We have to pay some charges to the distributors, the power distributors. Okay. So suppose if we are consuming power from the grid, we have to pay some monetary terms into the power distributors. And if we give power to the grid, we have to get power from the grid. Okay. So here one commercial, very important commercial points come, which is the further generation of, which is actually requirement of this microgrid and the power utility management system. So suppose if we are using power, so we have to give a fixed amount to the per unit per unit power we are consuming. So that power is fixed. Like suppose if we use 5 unit of power, we have to pay uh, per unit 5 times per unit power tariff. Okay, but if we have some excess power, so who are going to buy? This is not being managed. Suppose we have an extra 1 unit power in our home, so whom we should sell? This is not monitored. Suppose if we are in the house, we have 1 unit of power excess, to whom we provide. It is not like some transportable type of things, material things like we take and give to some other person. It is connected to the grid, and if we deliver some power, extra power to the grid, someone has to utilize it. Okay, and it is not like that. If we have very excess power, we can put all the power into the grid. This can't be there, because it's when you stabilize the grid. Okay, so if we, although we have some power, so those power may have, sometime it has its value. Suppose there's a shortage in grid and you have excess power. So if you supply to the grid, then power demand is very high and you can get more monetary benefits. But suppose if there's a excess power in the grid and you have excess power, but you can't supply the grid because they don't want the power, because the power in the excess grid is there. Okay. So whatever power you are having from your photovoltaic cells, its value is changing. Its value is time dependent. Suppose in daytime, in general, you can imagine in general, suppose or if your society is get uh, fully this installed photovoltaic cell, so all households are having excess power in the daytime. So if someone wants to sell their power in daytime, and particularly that time they maybe there is no wires, but in night time the power requirement is there. So you can imagine that whatever power you are having from your photovoltaic cell, its commercial value is varying. It's at different times commercial value is different. Okay. So that commercial value is need to be managed to optimally optimize your power consumption and power distribution. Okay, so for that optimization, for that optimization, there's some major advantage terms and the advantage technologies may come in the future. In this slides also you will get one snips of that management type of things. Okay, so for consideration, you can imagine like at what time. Suppose you just imagine one example. Suppose you have 5 units of power of your photovoltaic cell. Okay, and you have a grid power available in there, and grid power cost is suppose 10 rupees per unit, and you have a 5 unit of your power. So suppose in daytime you can purchase power from other person or other generation, or in the night time you can utilize your power. Suppose if the power cost is variation is there, so in this way you can optimize your energy cost. Okay, how you will optimize your energy cost we will discuss in later slide. Okay, but for this slide you can just take a carry forward that we have our own power, we have our grid power, so we have to manage both the power in the utility so that we can optimize our cost, the whole cost of our power consumption of our household. Okay, so move here that smart microgrid. Why smart microgrid comes into the limelight right now in this in present scenario? Because there is a possibility that you can have a computation system of very high grade in very low cost. Because right now, suppose in the future, if some computational system is there, you have to go to the computer system. But right now, in the phone itself has very much computational power system. Small chips have very much computation power capabilities and systems. So you can design from a very low cost. You can design a very rugged computational system from very low cost and very low these chipsets. Okay, and second thing is that right now consumers are shifting from AC type of things to DC type of things. Like previously, there's a bulb of filament based bulb, there's a bulb of CFL, all those things. Those are the AC type of things. But right now, the things are going to the DC type. How is the DC type going? Like previously, there's a CRT TV. So in CRT TVs, there's a requirement of AC power. Okay, or some high voltage DC power. But right now, whatever the TV is consuming, it internally is a DC. Like you're supplying AC and then the AC is being converted into DC and then its TV is running, and all those things systems like similarly those are running on DC power things. So the consumer utility devices itself moving towards the DC systems. Okay, so this is another advanced advantage point and point of interest, which is required to move into a smart microgrid, because microgrid basically it's more biased toward the DC system. And the third one is a decrease in photovoltaic energy generation cost. So this is also one point which drives the grid into the smart microgrid. Okay. So this is some model of microgrid. We can see that there is a photovoltaic cells and there is a wind energy. Then there is a grid interface which convert AC into DC, and then the DC utilities is there. You can also store DC into your battery depending on your requirements. So now we go to the consumer behavior. This is a very interesting point. You can note down it that why we are going into the consumer behavior, because we have to optimize our cost of energy for maintaining our households. So first we need to understand that what is the consumer behavior, and on the basis of consumer behavior we can design some algorithm which is very useful for the design this smart grid management system or this energy efficient management system. So consumer behavior, this is very simple terms. It maybe looks very fashionable term, but it's very simple that on what cost a person use energy. Suppose at this time the cost of fuel is uh, uh, is rising very high. So suppose the cost of fuel is rising very high, people are normally used to decrease their consumption of fuel. So similarly, if the energy tariff is, suppose right now it's a 7 or 8 rupees of energy tariff per unit, and suppose tomorrow the energy tariff increase to 50 rupees per unit. So alternatively, you will tend to consume less energy to maintain your cost, in the control. So this is the consumer behavior. So you can see in the x-axis there is energy tariff and y-axis is energy use. So on what tariff, what energy is being used. So you can see that as a different tariff has different energy use by the different consumers. So it is not like a fixed rule. Like if 10 rupees energy tariff, you're going to use 60% of your previous consumption. So if 20 rupees is there, you can use 30% of your consumption. So different people have different energy consumption tendencies, but based on the energy tariff. Okay. So this comes like distributed things, and you can see here if we collectively visit, collectively see the energy, the consumer behavior on the energy tariff, you can see there that in general, if energy tariff is increasing, the energy use is decreasing. You can see from this plot. So energy tariff is increasing, energy use is decreasing, but it can't go to zero because some it. So what is the this boundary line? So essential utility should be there. Suppose if you are using light bulbs or suppose some medical equipment is there. So whatever energy tariff is there, you have to use in essential utility. So that is the minimum boundary and maximum what you can use, whatever the maximum capacity of your the consumer this consumer like utility, suppose bulb, what fan. So maximum you can use that things also. Suppose you can your maximum capacity of use is suppose 5 watt or suppose 10, suppose 1 kilowatt. So you can use maximum up to 1 kilowatt. You can't use more than 1 kilowatt because all your utility can consume maximum 1 kilowatt. So suppose energy is tariff is go to zero. Suppose energy is being free, but you can't use maximum the maximum capacity. So in the maximum capacity and essential utility energy use, you need to vary depending on energy cost. So this is the consumer behavior. So from this plot we can see that the consumer tends to use lesser if energy tariff is increasing. And if energy tariff is decreasing, consumer used to use more energy. Okay, now. So suppose this we can discuss one thing more. Suppose in household you are having some AC, so AC consume more energy. So suppose energy tariff is increasing, you will try to adjust by decreasing the temperature or increasing the temperature, decreasing the use time of AC. And if energy tariff is decreasing, you will consume more AC or you can decrease more temperature. So this is the consumer behavior of based on energy tariff and energy use. Okay. So on this consumer behavior, we derive some algorithm, and that is very useful for designing the whole management system of the smart grid. Okay. So here you see that tariff is different. Suppose if you're living in some cities, so there are some localized DG cities also there, so like in some cities, because their energy cut, if energy cuts is there, you can switch to the DG generation because their energy availability should be 24 into 7. Okay. So localized DG generation set having more tariff is like 50 rupees or 30 rupees per unit rather than the grid tariff is 7 or 8 rupees per unit. Okay. So what the point of this slide is that the tariff of energy is different. Uh, the, suppose you're using DC sets, its tariff is more. Suppose you're using RD right now, its tariff is less and cost then decrease. Okay. So different energy source generation is having different tariff. This is the keep forward from this slide. Okay. And here you can just uh, get introduced to the concept of priority. Okay. So what is the concept of priority is there? Yeah. So you can see there is one analogy is there that on the same energy tariff on this the consumer behavior plot on the same energy tariff, two customers are using different uh, energy use because suppose there is a here is a the x-axis is same but their energy use is different. So suppose on same tariff, two consumers are behaving differently, and suppose so you can see that the one consumer using less energy, another consumer using more energy. So why this differentiation is there? Because both consumers have different energy priority. Suppose these consumers have more income, more salary is there, so they can obviously use more energy. Okay, so their energy priority is different. So consumer behaviors depends on their energy priority. Suppose some lesser income households there, they use the less energy on the same tariff, but some higher earnings households there, they may use higher energy on the same tariff. So this is the consumer behavior based on concept of priority, where they different consumers have different energy use priority. Okay, now. So what priority stands for, you can see here. So from here you can see that the priority function is there. The priority function depends on the priority of utility of at time t or stability of nth utility at time t, and t is the tariff at time t. So suppose if tariff is also varying at the different time, different tariff is there. So the whole priority, like suppose the bulb is there, so how much your probability that you will switch on the bulb, it depends on the how much your bulb's requirement is there. Suppose this is the night, if night time is there, so there is a requirement of bulb is more. Suppose time is day, so the requirement of bulb is less. So the requirement of particular energy utility, the electrical utility is different at different time. Like a bulb is there, so in the night bulb requirement is more, in the day bulb requirement is less. And also depends on the tariff. Suppose tariff is very high, so you will try to use less bulbs, less number of bulbs, or less number of time you can use the bulb. You know. So you can see that the priority function is depends on the utility of that particular consumables, that bulb or fan or tube light is there, or the tariff of power at that time. Okay. So the priority function is depend on both, like the usability of that and the tariff of that. Okay. Next, the tariff function, as we previously discussed, that tariff of electricity, it depends on the energy production source, like from what is the source of energy, like it's being generated from the DG sets or the photovoltaic cell or from the grid, and the energy demand at time t. So the grid, if there is more energy demand is there, so the tariff will be more. Okay, so it depends on both, like the energy source and demand on the grid. So tariff function depends on both, and by combining both the functions, you can see that priority function is combination of utility of that device, energy source of that device, and demand of the grid. So you can see that how you will behave. Like suppose the bulb is there, so suppose you are going to on that bulb, so you will see that first you will see that from which source the energy is coming. So suppose energy is coming from your DG generator, your it tends to be used lesser, or your priority will be less, that you will switch on the bulb. Second is that what is the utility of that thing. Like suppose if night is there, so you will need more, so you will most probably go to the turn on the bulb. And third is the demand of that demand at that time. So, okay, so all three things are combined and decide the priority functions. Okay, so this from the consumer point of view. Let's suppose there is a bulb in your house and you are going to turn on that bulbs. So turning on that bulb require these parameters to take into consideration to decide that, oh, okay, we go to turn on the bulb or turn off the bulb. Okay. So from there, you can see here that from these functions, you can summarize that if priority is greater than zero, priority functions, if you decide the priority function is greater than zero, you will turn on the bulb. And if priority function is less than zero, then you will turn off the bulb. So this is the optimal utility of your energy consumption. So this decides the optimal utility of your energy consumption, and how this decides. So see here, suppose this is a conceptual model, and for understanding this conceptual model, we will consider this one example. So suppose there is a this thing is a PIR sensor. So in many institutions and home, you can see the PIR sensors, bulb activation. Suppose if you are in the room, then bulb is on. If you go outside the room, bulb is off. Okay. So suppose if tariff is zero, suppose for the point of view, suppose if energy tariff is zero. So if energy tariff is zero, you will for economically you don't need to turn off the bulb. You turn off on all the bulbs, all the fans, all the utility, because energy tariff is zero, it can't disturb your energy cost. So if the sensor is triggered, suppose this time the here sensor is triggered, so it will turn on continuously to the infinite time because energy cost is zero. Okay, our priority is always higher because energy cost is zero, so you are not going to nothing lose. Okay now. So and second time, if priority functions is so tariff is changing. So if tariff is changing, so suppose here is priority the PI sensor triggers that is sensing that you are in the room, and then you are in the room. So by that time, how much time it will turn on the bulb? So suppose if turn on the bulb and its priority function is getting decreasing. So suppose this is time where its priority function gets negative. So this time from PI triggering and from this T on. So this is T on time the optimal utilization of your bulb. So by these functions, by this concept, by the power administrations, you can decide that how much T on is there. What is the T on? So T on is the PI function. There is T on the setting time. That suppose you go outside the room, it detects that you are going outside the room. So how much time up to that it will turns on. So that time suppose 60 minutes or 30 minutes or 30 seconds or 20, 10 seconds. So this T on you can decide based on this priority function to optimize your energy utility. Okay. So as you can see, the TN depends on the tariff and priority. So what this means that suppose because the whole microgrid system is very complex, so we can't control each and everything. Like we can't take so much data from each and every system, so each and every power generation and power utility or suppose storage is there. So what we can do that we can decide the priority of one consumable. Suppose bulb is there, so what priority of bulb is there. So priority is being suppose there's share market. Suppose some index is there. So index is it's calculating the strength of all the market, and based on the index we are taking the decision. So similarly, here the priority of every utility like a bulb is varying from the priority on and turn off the bulb. So by this way, we can control our equipment, our energy consumption. Or there is a big power battery, so this you can control. So this is this is so what it depends that there is a capacity and power, and third is the priority. So priority is an important term that being used to control the energy utility as well as the power flow. To understand more of this system or this concept, we go some experimental setup. Suppose this is a 3 BHK house, okay, and one user is there, okay. So this room, and this room, and this place is different place, okay. So this maybe have some bulbs, fan, and some TVs there, okay, and this also may have some bulb, fan, TV, or AC or whatever. So this all places are having some electrical utility. So suppose you just imagine that suppose we have one person is living, one person is live all places and live in the one or room or the kitchen or the room. You know. So not live all the time or all at any time, but all it live simultaneously or you just imagine there is a the bulb or fan whenever it is not in use. Okay, so that based on the the informations like the people are get more sensitized that they they consume less energy or they consume they build a habit to switch off the bulb or fan whenever it is not in used. But that is not actually in on a technical point of view that can't be much effective. We have to design some system, we have to design some algorithm that is control this that convert this habit into some setup, okay. And so right now there's a very much computational power is come into the small device, so we can have some system, we can design some system that is work like a way to save energy, to optimize your energy consumption. So in experimental setup we see here that how we are going to optimize our energy consumption. So suppose for the just for point of view, suppose this user is living in this room. So we can do one thing: we switch off all the electrical utility that is not essential in this room, in this place, and we keep on the electrical utility in this place. And suppose this person move to the this place, so see this switch on this place and this place and switch off this place. So similarly, we can manage the power use of this way. Okay. So what happens? Suppose this is moving in this side, suppose moving this side, suppose moving in this room. So depending on the time of spent, you can control the electrical utility in this room. So based on this, the presence of this person, the priority of all those equipments also changing. So suppose person is present in this room, the priority of bulb of this room is getting higher, and priority of bulb of this room is getting lower. Okay, because this lesser utility. So if you traffic is same, the traffic is same, and resource is same, but the utility of the bulb is this room is getting lower. So the priority of the bulb of this room getting lower. So if get negative side, this bulb getting switched off automatically. So this algorithm we can design. Yeah. So see here is some data of experiment. So this is experiment just uh, this experiment is being generated by the suppose this is actual power, this actual data, how it is being generated. We measure the strength of uh, hotspot, the phone this person carrying. So the hotspot strength is more if the person is in this room, and if we measure from the strength of hotspot, so here we get lesser the strength. So you can see here that this is more like so 4 point. This is 4 point. All the 4 points are getting the strength of this person's mobile phone hotspots to determine that how much distance is there from this side. Okay, now so you can see in much lesser quantity that this is the strength is getting vary. Okay, now so from this place, we can decide where is the person is orienting right now. Okay, so suppose this is more simpler way you can see. So suppose like we decide that this is the cutoff point. Okay, so suppose the person is within this place, the utility of this is getting on. Suppose the person is getting outside of this range, so the utility of this room is getting off. And by this, I can decide this point. Okay. So see here, this is the same thing that in pictorial representation we can see here. You can see here that the person is moving at different places. So by this way, we can optimize the energy use. Okay, now. So this is moving at different places, and based on the orientation of that person, the light is turning on and turning off. By this method, we can optimize the energy use. Okay. So see here, like this is the algorithm. This is more deeper. This is algorithm point of view. So this is like different places we having different. Like some suppose this is D point. So D point having four parameter of this. How four parameters? You can see here. This graph also at any point, at any point, at any point you can get four values. What is the value of the strength? So by these four values, you can decide which place is there. So by all four values, by comparing all four values of real time with the standard value, you can decide which place the person is there. This is more deeper than algorithm. So this is some other things that what this by this algorithm and this setup, we can see that what things we can do or we can done that can be done in future. That the microgrid system improve in the order of optimize the PV battery storage as well as the reduction of utility of energy consumptions, as well as the energy user can benefit by the buying energy trading and tariff based on the consumption as well as the power producers. So this is just the summary of that thing. Okay, so from here you can see that in future, like the how we using the power, how we generating the power is being different than whatever we see right now and we see it a decade ago. So both depends on the how the digital system, the computational system, and the power generation, and the tariff of the power generation is going to improve. Suppose right now you don't think much about the power consumption because energy is being under So like if energy is being out of your control, suppose energy charge is there right now 788 rupees per unit. Imagine if energy charge is like 50 rupees or 60 rupees per unit. So there you have to see some alternative energy source to fulfill your requirements of your household energy requirements, and that then there's times come when these smart grid systems and smart grid solutions, photovoltaic cells will come definitely come into play. Okay. And if any questions you can ask, I'm glad to give whatever possible solutions I can give you. So this is the end of the slides. Rajesh sir, you can take some questions, or if someone asks some question, I will try to.
So now I would like to invite Dr. Subho. Dr. Subho Upadhyay. Yes, there is one question. During the daytime, sunlight may be available. How the system know whether the person requires light to be switched on and or off?
Okay. So
Okay.
as I discussed that the priority function is there. Okay, na? So that priority function, suppose if sunlight is there and you're using all your this all your suppose you are using all your energy need from the photovoltaic cell, you are not using any power from the grid, and above even that you are having some surplus power and there is no purchase is there. So either you have to store that power into battery. Suppose your battery is also full. So even you if you not need a bulb, you have to switch on the bulb. So it depends. The utility using the bulbs, it depends on the current system, the current scenario. What is the current scenario is there? Like you can you use your power generated from the PV cells? Or can you store that power generation, or can you sell that power generation, or you have to buy some power generation is there? So that depends on that. Okay. Suppose your power is surplus and you're having lesser intensity in the room. So you can decide to turn on the bulb. You can have some smart system that measure your intensity of that room and it's on the bulb, turn off the bulb to maintain the standard intensity in the room.
One more question come in the chat box. How to identify the power coming from which source? All power coming from same line.
Okay.
Like multi sources are connected to with the same line. So yeah.
You can decide. You can't identify that which electrons coming from which source. You can decide. So it decides on the systems. So what it decides, like suppose there is a common suppose if you're considering your households. So if your households you are saying that your power is surplus, so suppose what you can do, first you have to use all your powers, and then if you require some more power is there, so you can take a grid power. So how it can done? Suppose DC system is there. So if this DC system going under voltage, okay, you can need more power to stabilize it. So power it can't decide. So if AC system, the power is being decided for the frequency. Suppose frequency of grid is going to the down, so there is demand in the grid. So frequency is going higher side into grid, so there is surplus power into the grid. Okay, now. So you can't identify which electrons coming from which source, but you can identify that there is a surplus or there is a shortage in the grid. So suppose microgrid is there, you can you can monitor voltage, and that voltage you can decide that the power is surplus, power is shortage.
Hello, am I audible to you?
I'm asking one question. I will give to you later. Let
Okay, okay, please. Your voice is
Yes,
not
yes.
audible.
Yes,
Right.
like the grid connections in India has different uh, uh, conditions. Like somewhere the grid is available for 24 into 7, like in
Are you
metro
audible?
city, and we also have the locations like. Yes, am I audible? Yes, I can hear you.
Yes, yes, please, please.
Yeah, like we have the different types of different locations based on we can categorize them based on the grid availability. So, like
Right,
there is any like remote areas or the urban areas like or the metro cities where the grid is available 24 into 7, but
right, right,
in few locations the grid is available for few hours.
right.
So, there is any like coming policy or the NTPC is taking any project for this type of location, like especially for the remote area where the grid is not available to install the solar system to integrate with the grid.
Actually, the policy is a government thing. So policy decision is a government type of thing. So as far as NTPC is concerned, so NTPC is taking care of its nearby areas. So try to supply the 24 into 7. But right now, your question is very valid. Like uh, because policy making is the government things, but policy implementations is things of companies or PSU. So, but right now that this microgrid is a very suppose previously that setting a powerhouse, setting a power plant is a very costlier things. But as the microgrid is concerned, so cost of microgrid is much lesser than the setting up the power plants. So these solutions comes from individuals. Some solutions comes from a startup or from a smaller MSME. So like for the examples, you can see that there is a inverter system. So inverter system is one of the example of these systems to making availability of power 24 into 7. So whole inverter system is a one package, and this solution is being provided by in the package from the different companies. So you can consider the inverter system is this thing like some a small micro if you consider these things. So the solutions may come like this way. So suppose for the one household or for one society, the whole solutions come by the different uh, MSME or some PSU, some government or some startup. This may come. This is a requirement of future, and this surely will come.
Yeah, I have developed the prototype systems for this type of
Yes, yes,
locations. I've considered
yes,
like the like grid is available for either day hours or sometimes night hours and try to optimize the cost and the sources. But
yes, yes.
my thing is like either the big industries are coming in this area or like they are planning to install this type of systems or they are limited to their power plants only. Means
Big industries it is limited to the power generations only. So, if as far as NTPC is concerned, so NTPC is set up is setting up the photovoltaic power systems, and this is supplying to the same grid. So we are more biased to the energy generation rather than energy solutions providers. So in future, maybe if some may acquire some companies, some startup uh, to the spread is on the mass level. So it depends on the whatever the real scenario of the future scenario and policies there.
okay.
So,
Subho sir, I think you have
yes,
some
sir.
questions. Yes, please.
Sir, you have nicely explained that how the tariff and the consumption pattern of different loads are being compared, means it is considered to be as an objective. But you have told that about the lamps, means bulbs will be there, load different type of loads will be there. There will be number of sensors. So if the number of sensors will be much more than how to, means it will be much more complex. Whenever the number of sensors will be there, much more data will be there. So how to solve this problem?
Yes, this is the main matter that this is the system is more complex and the solutions has to be find out. And this is the like an open area to have more research and more technology developments. This is the area of future that you have a problem statement, like you have more data, more census data is there. There is so at every point you have like generation point of the data is there, how much power is being generated, how much power is consuming, and how we're going to uh, design a system that is controlled. So this is the open area. So the startup has to come with the solutions or some technical being developed. So this is the area of futures. So so this is an open area. Like you can design so many technology and so many systems.
Yes.
Depends on.
Thank you. So any questions from the participants? Rajiv sir, your mic is muted, I think.
Yeah, please give the vote of thanks to our speaker. And Dilip sir, could you stop sharing the screen, please?
Yes, sure, sure.
Like, could you stop sharing the content? It's
Can you
taking
can you can you can you stop can you stop my this presentation?
Let me.
Okay.
I think from that side, I'm not getting that here. That thing can be done. I think it will be from your side. I'm not getting this option. And like in the bottom, you can see there is a share contents. If you click on it, it will automatically stop.
Okay. Let me try.
Disclosure to the video. Disclosure to the video. Stop video, and the next one is share. So just click on it.
Very very limited options I'm getting.
Okay.
Let me try one more time. Very limited options there.
Yeah, I think we can do one thing. Could you leave the meeting and then we can join? We
Yes,
can.
we can
Yeah, yeah.
rejoin. I can rejoin.
Yeah, because I'm also not getting same. I don't know why it is. It's happening first time. I get it.
Yes.
Okay, okay. Okay.
Okay, thank
So,
you.
with this, I'd like to give the vote of thanks to our distinguished speaker, Sri Dilip Kumar Choudhary, who is working at NPPC. So, thank you, sir, for
Thank you.
coming here and delivering your lecture on the topic of smart microgrid and utility optimization. So, thank you, sir. With this, we like to give a small virtual memento from our side and from the coordinator, Dr. Rajiv. So please accept it. This is a certificate of appreciation.
Thank you very much. Thank you very much.
Thank you.